Okay, I want to talk today about inverse functions and relations. So what is an inverse function, graphing inverse functions, and finding inverses of a function given the equation. So numerically, graphically, and algebraically. So first of all, an inverse relation. An inverse relation is formed when the independent variable is exchanged with the dependent variable. So the independent variable, remember, is x. So I can choose x from my domain, any x from my domain that I desire, and plug it into the expression or the function, and I'm going to get out something, and we call that output the dependent variable, which is the y variable, right? I input x from my domain and I output a y value, but that y value is dependent on my choice of x value. So if the inverse is a function, it is denoted this way. So note this is f inverse of x. So this is not the reciprocal, right? This is the name of a function, f of x. And this means the inverse of function f. That's what that notation means. So let's look at some examples. So for an example, is this a function? Well, I have x value 1, which is matched with 2, a 4, which is matched with -2, and a 3 matched with 2. So yes, it's a function. Every one input only gets me one output. So what is the inverse? And remember, the inverse relation is formed when you interchange or exchange the x and y variables. So in this case, it's going to be a set, and this is my x value and y value for the original function. So now I interchange, and this becomes x, and this is y. So my inverse is the ordered pairs 2, 1, -2, 4, and 2, 3. Now the next question says, is the inverse a function? Well, the answer is no. And the answer is no because what you can see here is when I input 2, I output 1, and when I input 2, I output 3. So for the input, x is 2, there are two different outputs or y values. Two different y values. All right, what about this one? Yes, it's a function. There's no repeating independent variable, right? The inverse, 4, -2, -4, 3, and -5, -8. That's set of ordered pairs. And is it an inverse? Is the inverse a function? Yes. I know because there isn't a repeating x value. So each x has its own output value. Every x has one y value, and only one y value. That's how we define a function. So next, let's go on to the next part, which is graphing inverses. And this might be the most confusing part, is the graphing, but it's also the coolest part. All right, every function and its inverse are reflections of one another across the line y equals x. So let me just graph that line for you. So it's sort of something like, I missed the stop, but anyway, goes through the origin, has a slope of 1. Right? Going through the origin, slope of 1. This is the line y equals x. So if I were to fold my graph on that line, then I would have the inverse function. Remember, a vertical line test tells us if a graph is a function. And the horizontal line test tells us if a graph is one-to-one. And the importance of one-to-one is that every one-to-one function has an inverse. So the horizontal line test tells us if a graph's inverse is a function. If a graph's inverse is a function. Right? It's called a one-to-one. Remember that to pass the vertical line test, you need that vertical line to only pass through the graph only once, because for every one x there can only be one y. And then the horizontal line test tells us if a horizontal line passes through the graph once, then it's a one-to-one. It means that my inverse, when I exchange x's and y's, every one x will have one y. All right, so for this example, the graph is indeed a function because it passes the vertical line test. However, it fails the horizontal line test, so when it says, is the inverse a function, the answer will be no. As a matter of fact, this is the line, this is the graph, f of x equals negative x squared plus 2. It's a parabola that has been reflected over the x-axis, then moved up 2 units. Right. So this graph won't have an inverse that is a function. Its inverse will be a sideways parabola, which will not be a function. All right, so if I were to graph its inverse, remember I need the line y equals x. That's my line y equals x. Now I'm going to try to plot this. Remember, find some ordered pairs. This ordered pair here is 0, 2. So right here we have the point 0, 2. So when I reflect that ordered pair, I get 2, 0, which is right here. And since that point 2, 0 falls on the line, when I reflect it, I get 0, 2. So they're reflections of each other. They're the same distance from this line y equals x. All right, this point is negative 2, 0. So when I reflect it, when I interchange x's and y's, I get 0, negative 2, which is right down here. Right. Also, here x and y are the same, all right, because they fall on the line y equals x and they fall on this red line. Then down here it'll be the same. So those points will be on the inverse graph as well. So the graph of the inverse is going to look something like that. It's going to pass through this point and go on this way. Right? So notice this is the graph of its inverse, but its inverse is not a function. In fact, the equation for the inverse is y squared equals, let's see, it should be negative y squared equals x minus 2, something like that. And remember, to solve for y, I would have to take a square root, which means I need to take plus or minus. So how do we get around this? And the way to get around this so that I can find the inverse of every function is to restrict the domain. So restricting domain. All right, restricting the domain so that it does have an inverse. So we had the function f of x equals opposite x squared plus 2, right? Opposite x squared plus 2. But remember, that didn't have an inverse that was a function. It had an inverse, but its inverse was just an equation, not a function. What if I wanted to write its inverse as a function? In order to do that, I need to restrict its domain. I need to decide what x values would make this function one-to-one. So remember, it's this way, then 1, then go down 2 over 4, 2, 3, 4. Nope. Sorry, 4 and then 2. 1, 2, 3, 4, 2, 1, 2, 3, 4, 2. The next would be 3 and 9, 4, 5, 6, 7, 8, 9. So right here, and 1, 2, 3 right here. So this parabola would look like this, something like that. All right, it's not a one-to-one function because it fails the horizontal line test. So how could I make it so it does pass the horizontal line test? So I can do that by restricting the domain. Just saying, yeah, for this function, every output can be found by inputting any number your heart desires, but then it's not one-to-one. So I'm going to say on 0 to infinity, right? So that means I'm going to erase this half. So you can't use any negative x values, which all of these are. Right? You can only put in x values like 2, 3, 1, 2, 3, 4, etc. You can only use those values. Now, find the inverse. All right, so to find the inverse, I'm going to draw the line y equals x. So this is the line y equals x. And I'm going to imagine reflecting it over that line. So this piece is going to come down here as a reflection. All right, so this piece right here, this was 0, 2, and 1, 1. Well, 1, 1, when you flip 1 and 1, you still get 1, 1. That point doesn't change. But 0, 2 becomes 2, 0. So 2, 0, sorry, 1, 1, 2, 0. This one was negative 2 and positive 2. Sorry, positive 2, negative 2. All right, so now it becomes negative 2, positive 2. Negative 2, positive 2. All right, so this point's no longer here. This point reflected here. This point stays the same. This point down here went up here. Then all of these points are going to come up here. And this little curve here is going to be reflected over this line as a little curve here, right? So this little curve and this little curve are reflections. And then this almost, it kind of looks like a straight line. It's not. What was this? This was 1, 2, 3, 4, 5, 6, 7, -7. And then this was 1, 2, 3. So this point was 3, -7, and now I'm going to have -7, 5, 6, 7, -7, and 3. So this point here. So now this, instead of being this way, it's going to start at the line and come up this way. Right? I'm a poor artist, but what I see is that I see this graph. Half of that sideways parabola, that's emerging. Right? It's what I would get if I folded the paper right along this line. This stuff goes here, this stuff comes up here, right? So that's how I find the domain when I have a function that's not one-to-one. Sorry, that's how I find the inverse function. Now this one, you might recognize the shape if I had a graph that looks like this is 2, this is 1, and then it went through -2, 2, 2, 1, 2. Okay. What you would notice is this graph looks a bit like the square root graph. It is in fact the square root graph, right? And it's a square root graph that's been shifted and reflected. So remember when I gave you guys the notes about shifting and reflecting, order matters. So this is f inverse of x now, and it's the square root of, to reflect it over the y-axis, that's a horizontal reflection, so it's negative x. Now to shift it to the right 2, remember we do -2. Okay. So we could write it this way, or we could write it as opposite x plus 2 if I distribute. So this function is an inverse of this function on the domain 0 to infinity, right? At any rate, I can't take any numbers that are any bigger than 2, because if I put in 3 here, I'd have an imaginary number. So it only works on the domain. This one only works on the domain from 2 to infinity, right? Notice that was our range here. Our range for the inverse, our range for the y value was 2 to -infinity. Sorry, and this should be -infinity to 2. Getting my values backwards. All right, so the range for the purple graph was 2 to -infinity for the y values. Now that became the domain of the new function. And the range of this new function is from 0 to positive infinity. And that's the domain we found here. We could probably just close that 0 off, right? All right, last thing that needs to be addressed is how to find the inverse of a function. So to do that, step 1 is to rewrite f of x equals, and then your equation would be there, as y equals, right? So just write it as y. Next, what we're going to do is interchange x's and y So now I have x equals some stuff that has y's in it, okay? And then finally, solve for y, okay? And this will be f inverse of x. To check, to make sure you got it right, first do f composed with f inverse, and then do f inverse composed with f. Both should have the outcome both should give you out just plain x. So let's see that in action with some examples. So for the first one, my first step is to rewrite it so it's y equals 3x minus 2. My next step is to change all of the y's to x's and all of the x's to y. So I have x equals 3y minus 2. X equals 3y minus 2. The last step is to solve for y. So I'm going to add 2. So I have x plus 2 equals 3y. Then divide by 3. So I have x plus 2 divided by 3 equals y. So f inverse of x is x plus 2 over 3. Now let's check. First of all, f composed with f inverse of x. Okay, so I'm going to rewrite my outside function, which is f of x. So this original function here. But every place I see an x, I'm going to write a parentheses. And within that parentheses, I'm going to write the inside function, f inverse. So x plus 2 over 3. Now when I multiply that out, 3 divided by 3 is just 1. So I'm left with x plus 2 minus 2, which is x. That one checks. So I will compose the other direction as well, because I should check both of them. So outside function is the inverse function. So I'm going to rewrite this function, but every place I see an x, I'm going to write a parentheses. So parentheses plus 2 over 3. Inside that parentheses goes the original function, 3x minus 2. Okay. Now when I drop the parentheses, since I don't need them anyway, I have 3x minus 2 plus 2, which is just 3x over 3, so that equals x. So this is indeed the correct answer, and I've just checked it. That's the inverse.